In this video, we're going to look at the concept of capacitance. Capacitance is something having to do with the storing of electric charge and storing of energy due to that electric charge being separated. This is different than what a battery does, and we'll talk more about that. And we want to look at how the voltages and the current in a circuit are affected by the stored charge in a capacitor. Capacitors come in a lot of shapes and sizes. The ones that we tend to use are cylinders for our experiments in class, but little teeny ones can also be found inside of circuits, integrated circuit elements. The schematic symbol is this. It's two parallel lines, not to be confused, of the same length, not to be confused with the battery, which is a long and a short line. Capacitors are used for a lot of things, but their function is that they store charge and then they release charge. Unlike batteries, which use a chemical reaction to push charge around and create a potential difference, capacitors are purely electric, and then they separate charge on two separate electrically isolated plates, and then they allow, when connected to a circuit, for that charge to leave. These are very useful devices for lots of things, but a basic capacitor consists of any two isolated conductors separated by something. A vacuum is the simplest to model, but you can also use another insulator, and we'll talk more about that. And then you attach a voltage source to them, and one side becomes positively charged, one negatively charged. Basically, you're pushing all the electrons to one side. Each plate, by definition, has to store an equal and opposite amount of charge, so they're kind of this symmetric thing. Usually, our capacitors, our quote-unquote real capacitors, are parallel plates, the ones we deal with. You can also make cylindrical and spherical. We'll talk more about those, but the ones we tend to use as our model are parallel plate capacitors, which, if you remember our study of electric fields, you would imagine you could create a pretty uniform electric field going from the positive plate to the negative plate. If they're close together and pretty large, the curves at the edges don't really matter, which is usually the model we use. I'm going to drop in here a demo of how we think of a capacitor charging up and what it does in a circuit, so you can see that. All right, we are going to look at a capacitor charging sequence. And so what I have set up is I've got a battery pack. I've got two bulbs in series with each other with a capacitor in the middle. I've got a voltage meter attached across the capacitor. I've got a current probe set up so that I can look at the current. This is the circuit, basically. We're going to start with no battery connected. And if you think about color coding, we're going to think about how for the initial case, there is no charge built up on the capacitor. There's no current flowing, which must mean that the circuit is all sort of neutral. All the wires are color-coded yellow, nothing going on. As soon as I connect it, I'm going to get red to blue, and I would expect that the capacitor is not yet charged up. So I would expect bright lights. And so that's what we're going to kind of see what is happening as we go through this. To also track this, I've got a current and a voltage probe. The current probe is reading zero current. The voltage probe, I'm just going to zero both of these out one more time. And we're going to collect data as we go. So I'm going to start collecting data, zero voltage, zero current going along there. And then as we go to this, so we can watch both at the same time, I am going to connect my circuit and start collecting data. Right? We start with bright lights, a spike, and then over time, the potential of the capacitor is building and building and building, and the voltage or the current through the circuit is decreasing. It started out at its maximum, and already you can see that these light bulbs have essentially gone out. There's still a little bit of current, there's still voltage, right, as it's approaching some final value. You'll notice that the current slope isn't perfectly flat. This, of course, is a non-ohmic. When the light bulb goes out, things change. We're kind of waiting until the voltage and current stop changing. The current is getting very, very low. The voltage or the potential is pretty high, approaching the battery potential, about 4.5, as the current slows down and slows down and slows down. So I'm just going to stop this in a couple seconds and say we have gotten the full charge sequence. And so if we flip back over to this picture, when the charging begins, the bulbs are nice and bright. We've got red to yellow and blue to yellow. But over time, the capacitor charges up and has now charge on it, which means that one side maybe is orange, the other is green. current is not flowing as strongly, and the light bulbs are not going to be as bright. And at the end, what we see now is that we have fully red to blue. The battery voltage and the capacitor voltage are the same, which means the light bulbs have nothing across them. Right? So that's the fully charging sequence. And so the reason the current stops flowing, of course, is that there is no potential difference across these light bulbs because all of the charge is stacked up on this capacitor. You can't push another charge onto it, at least the battery can't. So the next thing we're going to do is look at the discharging sequence. I don't know, I have that word no there, I'll cover it up. We're going to start by disconnecting the battery. So I'll flip back over to my picture, right, and to my graphical analysis so we can see kind of what's happening with the potential. And if I disconnect the battery, one thing you should notice is that even though the battery is disconnected, take the battery pack, remove it completely, we still have a voltage across the capacitor because it is fully charged. It has a voltage across it. There's no current, essentially, right? And what we want to do is we want to take a look at what's going to happen as time goes on. Well, if there is voltage across that capacitor, we need to go back and think about our picture. What does this look like when there is no battery in there? Well, if the capacitor is fully charged, right, with a bunch of positive on the top and a bunch of negative on the bottom, it has to be red to blue. But the bulbs are not lit. There's no current flowing through them clearly. And so it must be red on both sides of the bulb. And so we could move our voltmeter if we wanted to the two ends of that, and we could measure that we have the same voltage across the capacitor. Then, as we start to discharge it, when I connect red and blue together, I would expect that wire to go neutral. And so as soon as I connect it, I would expect still red and blue on one side, but now yellow. And over time, as the discharging continues, I would expect that as the charge gets lower, we would go to green and yellow, or green and orange with yellow still on that side, and then at the end, completely yellow. So we can check that out by flipping back over to our picture, our live readout, and our graph, and we can actually collect this data. So again, voltage across the capacitor is being measured, and we've got current flow that we can measure as well. I'm just going to zoom in on these a little bit so you can kind of see what's happening on them. Which is kind of interesting. So I'm going to collect some data, start collecting, and I am going to connect my circuit together. And notice that it goes bright. And what do we see? It jumps to the negative. And the potential, which started at a high value, is dropping. Right? These time sequences are a little bit skewed right now, but we can watch them as they go, right? This potential, this voltage is decreasing, heading towards zero. Notice now the light bulbs have gone out. The current is heading towards zero. You also see that bump that happens when the light bulb transitions from being on and off, right? That kind of ohmic switch. And now we're heading toward zero voltage. We're down to essentially zero voltage, as sensitive as our instrument is, and zero current as we go toward the end of time. So we can stop that. I'm actually going to show both of these data sets at once because although we didn't start them at the exact same time, you can see they sort of have mirror images of each other, right? The potential in the first case starts at zero and it grows and approaches the battery voltage. In the second case, the discharge case, it decreases down to zero. The brightness of the bulbs, which is power, right, current times voltage, is also going to be changing over time because at the end of both of these situations, there is no voltage across the bulbs and no current. But at the beginning, there's a big current and a big voltage. So that's kind of our picture of this. And then we'll continue on looking at our scenario. Right, there's the discharge. The one last sort of question, why does the current stop? Does the current ever flow through the capacitor? I'd left the no. And I'm back to this video form. So the current doesn't actually flow through the capacitor. Current flows in the circuit so that charge can build up on one side and then it can leave. And the current will only stop when the capacitor has reached its total capacity for charge, basically when it's gotten to a voltage equal to that of the circuit around it. So how does this actually work, and how do we determine how much charge we can store? Well, the basic relationship is that Q, the amount of charge that can be stored, is equal to C, the capacitance, times the potential, or the potential difference that you apply to the capacitor. We define capacitance as charge per volt, basically farads, coulombs per volt. That means that a 1 farad capacitor, which is what I used in my demo, is able to store 1 coulomb of charge for every volt that's applied to it. And I used 3 1.5 volt batteries, so that's about 4.5 volts, not exactly because they're a little bit old. That means I can store about 4.5 coulombs of charge in that 1 farad capacitor. All right, and so that's how we think of capacitance. The symbol farad is usually a capital F, and you'll see that on your multimeters if you play around with those in class. And there's actually 3 different ways we think of this formula. Capacitance is defined as charge per volt. If you're trying to figure out how much charge will be stored, if you know the capacitance, you know your voltage source, you can do that. Or finally, the voltage across a capacitor can be found by knowing how much charge you have stored and what the capacitance is. Okay, so that's kind of where we're at on that one. These capacitor equations are very similar to how we use Ohm's law and kind of look for the missing piece. So a quick example of this, how much charge will be stored in this capacitor? This is the example we did, right? 4.5 coulombs of charge, positive 4.5 on one side, negative 4.5 on the other. So these are big amounts of charge, right? We've been looking at nano and microcoulombs, that kind of thing. And the reason that this can be so much bigger is you're storing a lot of charge, and we are actually having the charges attracted to each other. The positive and negative are pulling each other towards one another, right? So we could do another example here. What's the one here? What do we get here? If we have a 0.1 farad capacitor, we only get 0.3 coulombs with a 3-volt battery. Does the resistance of the bulbs make a difference? It doesn't. It will change how long it takes for the battery to charge, or it's not the battery, the capacitor to charge, because current will be flowing more slowly, and that current is coulombs per second, but it doesn't actually change the final voltage. If you have multiple capacitors in a circuit, we can do what we've done with resistors and find an equivalent capacitance. The CEQ could be found by knowing the total charge in the circuit divided by the total voltage, right? And that would be something we could figure out if we could measure the total charge. The thing about the total charge is we normally measure current. And if we have a continuous measurement of current over time, we could find the area under that curve and we could find the total charge. But this is not always easy. So usually we think about adding up the capacitors first. When capacitors are in parallel, what does the charge do? Well, some of it goes onto capacitor 1 and some of it goes on to capacitor 2, right? So there's multiple locations for the charge to go. They are in parallel. The equivalent of this is as if you have given the capacitor a larger area. So the capacitances add as you go like that. So the equivalent capacitance in parallel is simply adding up the capacitances. The things that are important about capacitors in parallel are that they must have the same voltage. They could have different amounts of charge depending on their capacitances, but adding capacitors in parallel always increases the equivalent capacitance. So a quick example of this, if I have a 60 microfarad and a 20 microfarad, that's 80 microfarads of total capacitance. The 10-volt battery attached, that's 800 microcoulombs of charge. We can figure out that since the voltage has to be the same for both, we can calculate this for each individual capacitor, how much charge each one has, like that. What about in series? Well, in series, the charge goes onto one capacitor, right? And then it might push some off the other side and push it onto the other, but essentially you get a positive side and a negative side of the whole combination. The inner plate's charged by induction because no charge is going onto or off of that center section, right? So any charge that might leave one side just goes to the other. It's all in an electrically neutral area. And so what that means is this part of the circuit, right, is electrically neutral. It's uncharged. So negative Q1 equals positive Q2. So the charges must be equal even if the capacitances are different. And this is true for any number of capacitors in series. It doesn't matter if you just have two, like this picture, or a whole bunch. So what does that mean? Well, if the capacitances are different, but the charges are the same, then the voltage can also be different. And that's true of any series circuit element. The small capacitor has the bigger voltage drop, which is not how it works with resistors. And so because of that, if we use the loop rule, we add up the voltages. That's Q total over CEQ equals Q1 over C1 plus Q2 over C2. The Qs all have to be the same. And so these add as reciprocals. Capacitors in series must have the same charge. They could have different voltages. And if you add them in series, it decreases the CEQ. Right? So that leads us to capacitors. Measured symbol C for capacitor, measured in farads, capital F. They store and release charge. C equals Q over delta V. Delta V is Q over C. In series, they add like reciprocals. In parallel, they add directly. These are the opposite of resistors. So we still have two other pieces, the physical parameters and the energy of a capacitor, which we'll get to. But if you have a compound circuit, you use the same rules you always use for these kinds of circuits, right? You find CEQ for the whole circuit and Q total. Well, CEQ is first going to be the 2 and the 4 together to get a 6. That's in parallel. Add them in series, and you end up with 2 microfarads. The total charge for the whole circuit is 12 microcoulombs. We can then go from there and do the rest of it. Well, we know that the total charge is split between 2 and 3, and C1 has to have a charge equal to the total. There's my charge equation. All right, this is kind of like the junction rule because charge over time is just current. And so Q total is Q1, which is 12 microcoulombs. We can go a little further and say, well, the voltage then there is 4 volts. And by the loop rule, the other 2 capacitors have to have 2 volts. And then we can calculate their charge by using Q equals CV. So now we have all of our values, the loop rule, the junction rule. Really, the loop rule here is still safe, and we haven't violated any fundamental rules of physics. All right, so that is